Assalamu alaikum. My name is Najaf and my roll number is 21TE06. Today I will be discussing lab number 11 of digital signal processing. The lab objective is analysis of frequency versus Z-plane graph. Task number 1. Explain the graph output in terms of frequency versus Z-plane poles and zero. Design of a low-pass filter, and we have been given the following code. And the transfer function in the output will be shown as this. So here, num is the numerator coefficients of the transfer function, then is the denominator coefficients of the transfer function. This line here generates and displays the transfer function. The figure 1 creates figure 1 for the plotting. Frequency Z plots the frequency response of the system, and the figure 2 creates plot number 2, and Z plane shows the plots the zero pole of the system. So if we run the code, here we observe that the line transfer function generates and displays the transfer function, uh, and here we see this in the command window. And if we talk about the output in the figure 1, we see that this is the magnitude response of the normalized frequency, and this is the phase response. And in the Z domain, we have the plot of the zero and pole of the system defined by the transfer coefficients. Now task number 2, explain the graph output in the terms of frequency versus Z-plane poles and zero, and we have been given the code. Here we have defined the numerator coefficients of the transfer function, the denominator coefficients of the transfer function. The transfer function will generate the transfer function of the given numerator and denominator, and then we will plot the frequency response, and then the pole zero plot of the system. So when we will run the code, here in the output in the command window, we observe the transfer function, and in the this is the frequency response of the system, whereas this is the Z response, which shows us the zero and pole of the system. For task number 3, explain the graph output in terms of frequency versus Z-plane poles and zeros, and the code has been already given. So in the MATLAB, we see that we have given the denominator and the numerator coefficients, whereas A is used for finding the roots of the numerator polynomial, and B is used for finding the roots of the polynomial obtained from the previous step. This line here generates and displays the transfer function, and then we plot the frequency response and the plot in the Z-plane. So when we will run the code, in the command window we observe the transfer function of the system, and here figure 1 displays the frequency response of the system, whereas figure 2 displays the pole zero plot of the system defined by the transfer function coefficients. It shows the location of the poles and zeros in the complex plane. Task number 4, explain the graph output in terms of the frequency versus Z-plane poles and zeros, and the command MATLAB code has been given. So here we have defined the numerator and denominator coefficients, then we calculate the transfer function, and then we plot the frequency response and the poles and zeros in the Z-plane. So when we run the code, in the command window we will observe the transfer function of the system. The figure 1 will display us the magnitude and phase response, that is the frequency response of the system, and whereas the figure 2 will display the poles and zero plot of the system defined by the transfer function, and it shows the location of the poles and zeros in the complex plane, whereas the O represents the zeros and X represents the pole. For task number 5, explain the graph output in terms of frequency versus Z-plane poles and zeros, and the code has been already given. Here we define the numerator and denominator of the coefficients of the transfer function. For finding the roots of the numerator polynomial, we have defined the variable a. The variable b, however, will be used for finding the roots of the denominator polynomial. Then we will calculate and display the transfer function, and then plot the frequency response of the system and the poles and zeros in the z-plane. So after running the code, in the command window we will observe the transfer function of the system, whereas figure 1 will display as the frequency response, which includes the magnitude and the phase response of the system, and in the z-plane we will observe the positions of the zeros and poles in the complex plane. Task number 6, explain the graph output in terms of the frequency versus z-plane poles and zeros, and the MATLAB code has already been given. So we define the numerator and the denominator coefficients of the transfer function. Then we compute and display the transfer function and then plot the frequency response and the z-plane response. So when we run the code, in the command window here we can see the transfer function of the system has been displayed, whereas figure 1 will show us the frequency response, which includes the magnitude response, which is shown in the first subplot, and the phase response, that is shown in the second subplot. And in the figure number 2 we will see the that in z-plane we see the positions of the poles and zeros given by the transfer function coefficients. Task number 7, explain the graph output in terms of frequency versus z-plane poles and zeros, and this is the given code. Here we define the numerator and denominator coefficients of the transfer function, then we calculate the transfer function using this, then we will plot the frequency response and the poles and zeros in the z-plane. Here, if we see in the command window, we see that the transfer function of the system has been displayed. This is the discrete time transfer function, whereas figure 1 will show us the frequency response of the system of the transfer function, and the z-plane will show us the positions of the poles and zeros in the complex plane. And the position of the poles and zeros has been determined by the transfer function. Task number 8, explain the graphs output in terms of the frequency versus z-plane poles and zeros, and the MATLAB code has been given. So we define the numerator and denominator coefficients of the transfer function, then we will compute and display the transfer function, then we will plot the frequency as well as the z-plane response. So when we will run the code, here in the command window you can see that we display the transfer function of the system, discrete time transfer function. We will use the numerator of the transfer function to compute the zeros and the denominator to compute the poles. Here in figure 1 we plotted the frequency response of the transfer function, and in figure 2 we plot the zeros and poles of the transfer function. Task number 9, explain the graphs output in terms of the frequency versus z-plane poles and zeros, and the MATLAB code has been given. So here we define the numerator coefficients and the denominator coefficients of the transfer function, whereas a will be used for finding the roots of the numerator polynomial, whereas b will be used for finding the roots of the denominator polynomial. Then we will generate and display the transfer function, then we will plot the frequency and the z-plane response. So when we will run the code, we see the transfer function in the command window. And figure 1 will display us the frequency response, whereas figure 2 will show us the z-plane response or the complex plane response of the transfer function. Task number 10, explain the graph outputs in terms of frequency versus z-plane poles and zeros, and the MATLAB code has been given. So we define the numerator and denominator coefficients, whereas a and b will be used for computing the roots of the numerator and denominator respectively. And then we will calculate and display the transfer function, and we will plot the frequency and z-plane response. So when we run the code in the command window, we can see the transfer function of the system, whereas figure 1 will show us the frequency response of the system, and it will plot the frequency response of the system that is defined by the transfer function coefficients, whereas the z-plane plot will plot the poles and zeros of the system defined by the transfer function coefficients, and the cross will show us the location of the poles, whereas the O's will show us the location of the zeros in the complex plane. Task number 11, explain the graph output in terms of the frequency versus z-plane poles and zeros, and the MATLAB code has been given. So we will simply run the code, and we see that the transfer function has been displayed in the command window, whereas figure 1 will show us the frequency response uh, of the system defined by the transfer function coefficients, and the figure 2 will plot the pole zero plot of the system defined by the transfer function coefficients that will show us the location of the poles and zeros in the complex plane. Task number 12, which is also the last task of this lab, explain the graph output in terms of the frequency versus z-plane poles and zeros, and the MATLAB code is given. So we will simply run the code, and then we can observe that in the command window we displayed the transfer function of the system, whereas figure 1 will show us the frequency response, which consists of the magnitude and the phase response of the system, and the z-plane, the figure 2 will show us the z-plane plot that plots the poles and zeros of the system, which is computed using the coefficients of the transfer function. Thank you. That's it from lab number 11. I will see you in the next video.